In this video, I'm going to be talking about quantum memory. In general, quantum memory can be described as a device that can coherently store and recall information from arbitrary quantum systems. And when I say coherently, I mean that it should be able to preserve the quantum superposition state of the system. Now, this is quite a broad description. However, if we focus on areas where it has the most application, that is quantum computing, communication, cryptography, we start talking about qubits or qudits. Now, qubit is simply a quantum superposition of two orthogonal basis states, and qudits is higher dimensional, that is, we have more than two of these states. A very popular choice for creating these systems are photons. For good reasons, like we can use various properties of photons to encode our information. They can travel in free space and optical fibers, which makes it compatible with our current communication infrastructures. So we're going to introduce the term optical quantum memory, which is a system utilizing these qubits or qudits, and its states can be prepared and coherently manipulated using electromagnetic fields. So from now on, we're going to specifically be talking about optical quantum memories. Since we're dealing with arbitrary quantum systems, we can't really make a perfect clone and keep a copy, and this is restricted by the no cloning theorem. However, it is possible to create imperfect and probabilistic copies. We're not going to be discussing that, but we can think about some systems where theoretically we can store and recall entire quantum information. So here are two plausible ideas. The first one is straightforward. You can somehow contain the entire quantum system and release it when you need it back. The other option is to coherently map all the quantum information from this system onto another quantum system. But in this case, our original quantum system must be entirely eliminated after complete mapping. Otherwise, we would have made a total copy. In the first case, we have simple ideas like having an optical fiber loop or a cavity in which, for example, we can use the polarization of the optical pulse to trap and release it from the cavity. For the second case, we use some sort of a medium. These are usually warm or cold atomic clouds, Bose-Einstein condensate, or rare earth doped crystals. What really makes it a quantum memory is the reversibility of this mapping. That is, we're able to map back and reproduce our optical signal. Broadly, we have two categories of schemes. So the first kind are optically controlled schemes. So let's say that this is our medium, and the idea is that we use strong optical control fields to control the absorption of photons into the medium. This allows us to map our optical quantum information into the atomic information and back out as an optical quantum information. However, we also observe some added noise due to this control beam. Now, the other scheme is engineered absorption, which is based on a phenomenon called photon echo. So in this technique, we don't need a control beam, but the idea is that atomic transitions have some line width corresponding to their absorption features. And this technique relies on having different line widths in different atoms, or what we call inhomogeneous broadening. So this can be natural, or we can control how the broadening is spread over the medium. We won't be able to discuss all the details, but we're going to look at a simple example. So let's say that I apply an external magnetic field to my medium, and for example, let's say that this has a linear gradient in space. This would result in a very controlled inhomogeneous broadening. This means that each spatial position of an atom corresponds to absorption of different frequency components of the input pulse. This scheme is called the gradient echo memory, and effectively the information that you're storing in your atoms is the Fourier transform of your input pulse. So what sort of happens is that, let's say that this is our atomic information, so it's sort of indicating these intensities at different spatial positions. And I've made a cartoon plot in the k-space or the frequency space. And when the gradient is on, this atomic information starts to dephase or travel in k-space. Then we invert the gradient, and the information starts to rephase. And as this rephasing information reaches k equals 0, the rephasing is complete, and we get a photon echo. That is, we immediately have a photon being emitted, and over time the entire pulse is emitted. Now, there are a few hybrid schemes that aim to combine optically controlled and engineered absorption schemes to enhance efficiency. One such effect combines a Raman effect in atomic transitions and the gradient echo memory, and we call that the Raman gradient echo memory, and this was first demonstrated at ANU. Now, there are a lot of considerations and fine details if we start talking about the efficiency of different schemes. And the kind of memory that you decide to use depends on the application and available resources. So before we conclude this video, we'll briefly look at some applications. In the next video, we'll be talking about a popular choice of atomic energy level configuration to implement quantum memory, which are the lambda type 3-level atoms. We will have an overview of the quantum mechanics and what really is that atomic information. It will lead to the discussion of electromagnetically induced transparency, Raman interaction, and Utler-Town splitting. Finally, here are some applications. An application in long term would be to use it as a memory for a quantum computer. They can be used as quantum repeaters to mitigate the loss due to fibers in long distance quantum communication. There are a lot of applications in quantum information processing like temporal beam splitting, like temporal Fourier transform, which was recently demonstrated using GEM. Another important use is that they can act as a deterministic single photon source and detector, which has a wide variety of applications. If you're curious to learn more about these, feel free to look them up. There's a great amount of information on the internet. Alright, see you in the next video.